Welcome everyone. This is, as was said, the first in I believe it's 10 lecture series about the primary quantum sensors that are immediately relevant to the DoD. So we're going to start off this lecture series about Rydberg atoms, but the goal here is to try, this is the Quantum for National Security Committee of QED-C. And we have a large membership base that extends from technical experts that actually do sensor development through business folks that are trying to understand export controls and international trade, diplomats, strategists trying to understand how these sensors are going to impact networks. So the goal here is to try to give a level setting series of lectures roughly at the undergraduate level from a technical field. We're not assuming that you know quantum mechanics, but we are going to try to teach you what you need to know so that you can be a part of these conversations in this exciting field. So I can't think of a better person to get that started than Tom Gallagher. There's a reason that I asked him to go first. He was a professor of mine when I was an undergraduate, and one of my favorite classes that I took. And it just so happens that he is the person that wrote the primary textbook for the Rydberg field. So you're getting one of the best people, and that theme goes throughout the lecture series that we will have. So these are the various lectures and speakers that we'll have, and similarly, we have some of the best people to give you introductions to each of these sensors. So the goal here is to level set technology understanding as well as drive interest in QED-C and Q4NS. Every lecture that you see that has a little asterisk next to it is open to the public, as long as people make a request to me via email. So please do share the invites with your friends, let them know this is happening, and tell them to reach out to me if they would like to attend these lectures. So with that, just to not take up any more time, I'll go ahead and introduce Professor Gallagher. So Tom Gallagher is a PhD from Harvard in 1971 and has been a professor of physics at the University of Virginia since 1984. I believe he's technically professor emeritus now. Won the Davison-Germer Prize in 1996. As I mentioned before, wrote the book on Rydberg atoms that those of us in the field developing the sensors, regularly refer back to. Fellow of the American Physical Society, Optical Society of America, and editor for many journals. In other words, he's the right guy to give you the introduction, and so I'm going to hand over to him, and he's going to speak for roughly 45 minutes and hopefully have enough time for some Q&A at the end. So, Tom, I'm going to stop sharing, and if you can share your slides, I will go on mute.
That was a very generous introduction on your part. Thank you very much. And so I will share the screen. So what I would like to do is today is briefly summarize some of the notions that go into using Rydberg atoms for microwave and RF detection. So I will begin by introducing Rydberg atoms and a few of their relevant properties, and then including how people have, in fact, observed microwave and RF transitions before. And then I would like to introduce the dressed or atom field states and how they connect to driving microwave transitions. It turns out that this is not only interesting for driving the microwave transitions, but it's useful to understand how electromagnetically induced transparency works, which is the technique that's being widely used now to detect RF and microwaves. And then finally, just briefly mention how this is used to detect microwaves and RF. Okay, so a Rydberg atom actually is an atom in any state of high principal quantum number n. So that means since the energy is given by the Rydberg constant divided by n squared, where the minus sign means it's a binding energy. So the binding energies become very small. And so whereas the ground state is down here shown by the red line, in the Rydberg state, the classically allowed region that the electron can wander around in is much larger because it's in this Coulomb 1/r potential. So in fact, the allowed orbital radii increase as the square of the principal quantum number. Okay, so a Rydberg atom basically is an atom with an electron in a large, weakly bound orbit. Okay, and at n equal 30, just to pick an example, the binding energy is 13 millielectron volts, and the orbital radius is 450 angstroms. So these atoms actually have really exaggerated properties that let you see some phenomena that weren't so visible in other contexts. And we'll see some examples of that. So the properties of the Rydberg atoms pretty much scale with the principal quantum number. And I would like to just hit a few of these. We've already noticed that the binding energy scales as 1/n squared. So the spacing between the levels is just the derivative of that. It's 1/n cubed. The orbital radius we've already seen is n squared. But since if the electron is 400 angstroms away from the positive ion core, this means that you have a dipole moment that is 400 times an electron times the Bohr radius. Okay, so they have enormous electric dipole moments. So at n equal 20, the dipole moment is about 100 times larger than the dipole moment in the most polar molecule. Okay, so then since the radius goes up as n squared, the cross-section goes up as n to the fourth. And so at n equal 20, the geometric size of the atom is 160,000 square angstroms. Okay, so this is just absolutely huge. Another property that turns out to be important for us is the radiative lifetime and of low L states which are optically accessible. And they scale as n cubed, which is, I'll come back to that in a second. That's a little bit surprising since we're going up in energy and the lifetime is getting longer. Okay, so I think the best illustration of the sort of exaggerated properties of the Rydberg atoms is the way that they're detected in many experiments, or have been prior to electromagnetically induced transparency. That is to use field ionization. And so this picture is a picture of the potential that of an electron, or potential an electron sees, which is a combination of the Coulomb potential minus 1/r and a field E in the Z direction. So this is a slice of the potential through the center of the atom. So as shown in this picture, an atom in the red state will ionize and one in the black state down here will not. So, and in fact, if you assume that there's no Stark shift, which is a marginal assumption, you can easily show that the electric field required to ionize the state is 1/16 times n to the fourth. Those are in atomic units that I'll define in a second. But for n equal 20, this is a 2 kilovolt per centimeter field. Okay, so 2 kilovolts per centimeter is a field that is easy to produce in a laboratory. If you wanted to ionize the ground state, you would have to produce a field of 3 times 10 to the 8th volts per centimeter, which is not so easy to produce. Okay, so as promised, I will define the atomic units. So an atomic unit is basically whatever that quantity is in the 1s state of hydrogen. So mass is the electron mass, charge is the electron charge. Energy is twice the ionization potential of hydrogen, that is twice the Rydberg constant. The unit of length is the radius of the first Bohr orbit, which is just the Bohr radius. And the unit of electric field is the field that the electron feels at that radius, which is 5 times 10 to the 9th volts per centimeter. And in atomic units, Planck's constant, h bar, is 1, which means that angular frequencies and energies are identical. Okay, so I would like to just draw a picture of a hydrogen atom and a sodium atom. So in the hydrogen atom, I have an electron that's circulating around a point source, okay? And in the sodium atom, it's circulating about an extended source, which is composed of a nucleus of +11 and 10 much more tightly bound electrons. So as long as this electron in sodium is way out here, it doesn't really notice the difference between sodium plus and a proton. But in fact, if the electron comes close to the core, it in fact can sense the fact that in fact it's not just a point charge. And in fact, then as a result of this, the lower angular momentum states of sodium that have highly elliptical orbits, not like this, but more like this, are depressed in energy from the hydrogenic levels. And that's shown here, where I've shown the energy levels of hydrogen. These are the principal quantum numbers, which determine, that's all that's required to determine the energy in hydrogen. And I will later start using these letters so L, the angular momenta are from 0 up to n-1. And an angular momentum 0 state is an S state, 1 is a P state, 2 is a D, 3 is an F, 4 is a G, and so on. So in sodium, the higher L states, that is L of 2 and higher, are almost exactly degenerate with hydrogen. But you can see that the P state is lower and the S state is lower yet. That's because the electron in those states is not kept away from the core by the centrifugal barrier. And in fact, the electron samples goes inside the core and sees more of the unscreened nuclear charge. Okay, so here I've defined, the usual way we describe L, but N is the principal quantum number, L is the angular momentum quantum number, and M, which is not shown here, is the Z component of L. I will generally consider states of M equal to 0. So let's go back to some of these properties of the Rydberg atoms. One of the most surprising one is that the lifetimes become longer as you increase N and therefore increase its energy. And so why it has this sort of surprising behavior, you can see from just considering the spontaneous emission rate on any given transition, say from the upper to the lower state. It's the product of mu, the electric dipole matrix element connecting the two, squared, and the frequency cubed. Okay, well, this is the dipole matrix element written out for you. And if I consider, say, a P state, it turns out that it can decay to it can decay to any of these states, but in fact the mu q term, the omega cubed term, basically it completely dominates it. And so you can see that it doesn't really matter whether I start from this state or one up here. Omega is basically the same. So there's no so the omega has no frequency dependence. There is a dependence on N of the electric dipole moment, because the electric dipole moment between this G state and some high-lying state is completely localized in the region near the origin. Okay, it's where the G state is. And so as a result of that, excuse me, that matrix element simply reflects the normalization of the excited state wave function at the origin. And that normalization scales as n to the -3/2. When you square it to put it into this spontaneous emission rate, you then wind up with our lifetime, with a rate that scales as 1 over n cubed, or a lifetime that scales as n cubed. So it's simply the fact that when the electron is in the Rydberg state, it doesn't come into the core very often. It doesn't spend much of its time near the core, where it can radiate to the ground state. Curiously, if you consider a state of very high angular momentum, it only has available to it transitions to nearby states. And so the dipole moment turned out to be n squared, roughly the size of the atom, and the frequencies are 1 over n cubed. And so it has this n to the 5th dependence. So these lifetimes become really long. Okay, so at zero, what I've just shown you is true at 0 Kelvin. Okay, that is, a decay to the lowest lying state is always a dominant feature. At room temperature, there's considerable redistribution to nearby dipole coupled states. I mean, prior to people studying Rydberg states, nobody ever worried about thermal radiation and atoms, but Rydberg states like thermal radiation. So an example of this is say the 18S state of sodium. This would have a normal 0 Kelvin decay rate of 1.6 times 10 to the 5th inverse seconds, or a lifetime of about 6 microseconds. But in fact, at 300 Kelvin, it's driven to these other nearby P states, okay? And at rates that are not insignificant compared to the normal radiative decay rate. So, and the other thing that's true is that, of course, you can absorb a photon. You can absorb a black body photon and go up in energy, or you can have stimulated emission and go down in energy. So black body radiation drives atoms not only down, but also up. And so finally, when you can take into account the black body decay rate, the total rate here is 2 times 10 to the 5th, up from 1.6 times 10 to the 5th. So it's sort of like a 25% increase. And so this population is being shoveled out into these other states that you weren't thinking about. Although you might have used a laser to excite this state, you very quickly have all this other stuff. Okay, and this picture basically shows you how the spontaneous decay rates are distributed. Most of it goes to the lowest lying state. These are the n of the final state. And the black bars show where the thermal radiation goes. It goes into these nearby states that have big dipole moments connecting them to the initial 18S state. So an interesting thing is, if I go out to the state n equal 18, L equals 17 state, okay, that's the highest angular momentum state. The spontaneous emission rate is only down to n equals 17, L equals 16. That's shown by the white thing. This isn't quite right. Whereas the black body radiation in this case goes down also to that same state, and then up to the n equal 19. So it goes from 17 to 19. And in fact, these two rates are in fact far larger than the 0 Kelvin rate. These are now the dominant rates. Okay. So the higher the L state, the worse the problem of black body radiation is. Okay, so I'd like to move on to observing microwave transitions, excuse me, between the Rydberg states. So let's imagine I want to drive atoms from an NS state to an MT state with a microwave pulse of length t. So an excellent example of this was done by Serge Haroche and his team, which they excited with pulse lasers sodium atoms to the 23S state, drove the microwave transitions to 23P and to 24S. And this was done in a beam. So they had a beam of sodium atoms crossed by these two laser beams, and also a microwave beam from the side, and then a ramp voltage was applied to the bottom plate. So I'll come back to that in a second, but just to give you some better picture of what this looks like. So all of that was shown in the previous slide is encased in a vacuum can, and their source of ovens is a small stainless steel tube with a hole in it that they heat. And then they apply a voltage pulse to this upper plate that drives ions through a grid in the lower plate to a detector in the bottom. So And then finally, this can over here, which is 18 inches in diameter, is a picture of a real apparatus. Okay, so the way their technique works, because they can selectively detect, say, the higher lying red state here and not the black state. Okay, that's the principle of their technique. So the experiment works by having pulse lasers, microwave pulse, about a microsecond, and then a field pulse rising in a few microseconds. So since the 23P and 24S states lie higher in energy than 23S, they're ionized first, and you get a signal pulse from them here, and the 23S atoms will come later. So if you simply set a gate right here and scan the microwave frequency, you can in fact find the resonant transitions from 23S to 23P or 24S. And those are shown here. The two on the far right here are the transitions from 23S to 23P. And this one is a 1 over is a 2-photon transition, which the interesting thing is, if you read in the caption here, they point out, whoops, that the power here is 10 to the 7th higher than it is here. Okay, I mean, it takes absolutely no power whatsoever to drive these transitions. Okay, all right. So in principle, detecting microwaves this way is simple, but it's a fairly complicated apparatus. So finally, I come back to the other question. The geometric cross sections of these atoms are enormous. And so what role, if any, are collisions likely to have? Okay, so I'd like to sort these collisions into two kinds. One are long-range collisions in which the collision partner interacts with the whole atom, and then we can consider short-range collisions in which the perturbing atom might interact with the electron cloud or the ion. So I'll consider these first. So in fact, it's the interaction with the electrons that's the most important. And so if I have an argon or some other atom that wanders into the orbit of a Rydberg electron, the Rydberg atom basically scatters from it elastically. I mean, okay, so just imagine a ping pong ball scattering from a billiard ball. So what happens is it scatters elastically and goes off in a new direction. And so what that actually corresponds to in terms of the atomic state is that I get mixing of the degenerate, I can have mixing of the degenerate angular momentum states. So if you look at the rubidium NF states or the sodium ND states that are almost degenerate with the higher angular momentum states, you in fact find cross sections that are almost as large as the geometric cross section, up to about n = 20, and then they go down. Okay, so these cross sections are probably not really going to be a problem for making a Rydberg receiver. On the other hand, you can have collisions between Rydberg atoms, and they can have problems. And so I would like to show you some experimental data of collisions of two sodium atoms that are at thermal energies. And this process is also studied in cold atoms, and they're called often Forster resonances there. But in this particular case, sodium atoms in a beam were populated in a beam. And so collisions, sodium atoms in a beam were excited to populate the 17S state. So collisions occur during this time, and the fast atoms hit the slow atoms, and then a field ramp is applied to ionize the atoms. And basically, using the time-resolved field ionization signal, atoms which have gone up to the 17P state can be discriminated against versus the 17S because they will ionize sooner. And so how they get up to the 17S state is that one 17S atom collides with the other one. One takes energy from in an amount that's given to the other energy. So no energy has to go into the into the heavy particle motion. This is in fact a resonant dipole-dipole collision in which one of the atoms acts like a microwave field driving the transition in the other atom. Well, anyway, as I said, I wanted to claim that this has been observed experimentally. And if one looks at the population in the P state, as this tuning field is varied, you observe these 4 peaks as expected. And so just from the field variation, it's easy to compute the collision time. They collide for about a nanosecond. The most interesting number from our present point of view is the collision rate. To see this signal at all, the collision rate had to be something like 1 per microsecond, which is the product of the number density to cross-section of velocity. So I know the number density, I know the velocity, and from this, solving this, I can find the cross-section, which turns out to be 1 billion square angstroms. Okay, that sounds, of course, completely absurd, but it's actually right. Okay, and this can actually be a problem, or this kind of process can be a problem in a Rydberg receiver, because the cross-section is basically given by the cube of the principal quantum number. That's the geometric cross-section, sorry, the 4th power divided by the velocity. So black body radiation produces just the resonant collision partners that you need. You don't have to have a tuning field. Black body radiation will drive D atoms, for example, to nearby P and F states that have big dipole moments for these transitions. And then I can, in fact, have this D atom collide with that P, and they can exchange. It's always resonant, so this will always be there. And if you get to the point where there's a reasonable population in the Rydberg state, this can be a problem. Okay, so now I would like to move on to describing microwave transitions in an atom field picture. So we first want to find the atom's wave function, which we do by solving the Schrödinger equation. Okay, this is the Hamiltonian operating on psi must be equal to its energy psi. So this has solutions with the quantum numbers n, l, and m that I've already introduced that are products of a radial function that depend on n and l, and an angular function, which is just a spherical harmonic. Okay, so the first few spherical harmonics are shown here. They're basically functions of order 1. The ones that have L even are symmetric on if I take theta through 180 degrees, whereas the odd ones are not. They go to minus themselves. And the radial functions look like this. So these are n equal 10 radial functions for P and S. And as you can see out here at large distance, they look pretty much the same. And they go out to something like, well, in this case, almost 2 times n cubed. Okay, so what I would like to do is to use the wave functions for these atomic states as the basis functions to find solutions when I add a field. And so to find the eigenvalues and therefore the eigenvectors, we diagonalize this Hamiltonian matrix. So if I have unperturbed NS and NP states, that is no external fields or anything else, the Hamiltonian matrix just looks like this. I mean, it has the S energy and the P energy. And this is operating on state vectors that have the components of S and P. Okay. So now I want to consider adding an electric field in the Z direction that produces this interaction energy that looks like R ZE, which is R cosine theta E. So when you compute the Hamiltonian matrix elements, which look like this for the NS and NP state, you find that for NS going to NP and NP going to NS, they look like n squared times E. Okay. But if I compute the matrix element between NS and NS here, replace this NP with NS, I get 0. And that basically it's because this function is even with respect to theta, and when I throw in this theta and do the angular integral, I get 0. Okay, but in any case, now our Hamiltonian matrix looks like this. Okay, so in hydrogen, these two energies are the same. So we're going to remove that energy, and we get the following matrix, which is easy to compute. It has the eigenvalues of plus or minus n squared e, and the eigenvectors are psi and s plus or minus psi and p. Okay, pretty straightforward. And so the two eigenstates have permanent dipole moments that are aligned either with the field in this case, oops, or against the field in the other case. And if you can, in fact, compute the expectation value of z, and it's, oops, it should say plus or minus n squared here. Okay, so now I'd like to consider NS and NP states that aren't degenerate, which is true for everybody but hydrogen. So for sodium and rubidium, this is certainly true. They are, in fact, separated by an energy omega, and I want to couple them by an Z-polarized microwave field, which is given by E cosine omega t. So the time-dependent wave functions of these two states look like these two expressions right here. Now these are the spatial wave functions, and the time parts only differ by a factor of e to the minus I omega t. So we can reduce this problem to the static field problem we just considered by introducing atom field states, sometimes called dressed or Floquet states. So the NP minus 1 state is the NP state with one less photon in the microwave field, whereas the NS state has the original number of photons in the microwave field. So the NP minus 1 state is degenerate with NS minus 1. They're degenerate with each other. And if I express the microwave field E cosine omega t in terms of these two exponentials, I use the resonant imaginary part that cancels out the e to the I omega t in the p state, and I wind up with a Hamiltonian matrix that looks like this. Okay? This is essentially what's called the rotating wave approximation. So I once again subtract their common energy, and I have this very simple matrix, which I can diagonalize. And I once again find that I have energy eigenvalues are plus or minus the dipole matrix element times the field amplitude over 2, or which I will call plus or minus omega over 2. Omega is the splitting between the two. The eigenstates are then these combination of S0 and P minus plus or minus P minus 1. It's essentially identical to what we did in a static field for hydrogen. So if I look at the atomic parts of these eigenstates, they look like this. It's psi s plus or minus e to the I omega t. If you calculate the expectation value of z in these, you in fact find that it is z cosine omega t, which is essentially tells you that in the eigenstates, they have dipoles that are oscillating synchronously in phase with the microwave field, or exactly out of phase, leading to these non-zero time average fields. I should be a little bit more careful. It's not just by time average, I mean it's averaged over at least over an integral number of cycles of the microwave field. Okay. So if I wish to drive the microwave transition from NS to NP with a microwave pulse of duration t, what field do I need to do this? Well, when the microwaves are suddenly turned on, this NS state that I'm starting in is projected onto these two states as so. And at any later time, the wave function looks like this. These plus and minus states evolve in opposite, their phases evolve in opposite directions. And the wave function looks like this. And if you compute the probability as a function of time of being in the S or the P state, they look like this. So the population oscillates between NS and NP at frequency omega, which is often termed the Rabi frequency. And basically, to drive the transition at that time requires that this be equal to pi, which then gives a pulse of this form the name a pi pulse. If you've heard that, that's the origin. Okay, so I would now like to consider what the spectrum would look like if I were trying to drive the atoms from state P prime to state S. First, without any P state. Well, if I scanned this microwave frequency and looked at the S population, at the resonant frequency, I would see a spike. If I now add the microwaves, coupling S and P, this single line turns into a pair of transitions, which are spaced by omega, which is often also called the Altler-Town splitting. This is the same as the Rabi splitting. Okay, so this concept turns out to be important for us several times in electromagnetically induced transparency. So I would like to use, or to now move on to electromagnetically induced transparency, which, by the way, is enormously simpler than using the beam apparatus that I showed you earlier. So it requires two lasers, a 5S state to 5P laser at 780, and 5P up to the Rydberg state, which would be about 480 nanometers. Okay, so these are there are several hyperfine levels I didn't show there, but what I would really like to show here is the apparatus. So the apparatus is a glass cell containing rubidium. It's about 1 inch in diameter and 4 inches long, and they, in fact, here have some shielding. But the important thing is that I send the 780 beam through it in one direction, and the 480 nanometer counterpropagating probe beam goes through the other way, and it's detected with a photodiode. So what is then observed is shown here on the left-hand slide as you scan the probe laser. So if you didn't have the coupling laser on, you wouldn't get these blue features. You would just have the red line, which is the Doppler-Broaden absorption of the resonance line of one of the 4 resonance lines of rubidium. Adding the blue coupling laser produces these peaks, which are the electromagnetically induced transparency peaks. Okay, so where do they come from? Okay, so how EIT works is best understood by using these atom field states that we've just been talking about, except we're now going to use the ones that are created by the 480 nanometer laser, which couples the 5P and ND states. They're essentially the same as the ones with the microwave field, but there's an intrinsic difference, which is that the 5P state has a finite short lifetime of 25 nanoseconds, okay, whereas previously considered the states to be more or less infinitely long-lived. Okay, so adding the 480 nanometer laser splits the 5P and 44D states, shown by these dotted lines, into this pair of Rabi or Altler-Town split levels, psi plus and psi minus. So they're given by, so psi plus and psi minus are given by these expressions, which are exactly the same thing as what we wrote down earlier. So if you actually look at the spectrum of the 5P state from the ground state, it would look something like this. And basically, these two levels are overlapping with each other. Now, why that's, and they overlap because of the fact that this state has a finite lifetime. Now, it turns out that these states are coherent with each other. And so in the region where they overlap, you in fact have to add the excitation to the red state and the blue state. But in fact, those two excitations are out of phase with each other by pi. And so they cancel. And that's why you get the peak, the peak in between the center of these two lines. And so that's the origin of this peak. It's the cancellation of the excitation to the to each of the two dress states. Okay, so all right, now if I want to detect microwaves using Rydberg atoms, how am I going to do it? Well, it's pretty easy. You simply have to add a microwave horn looking at your cell. Of course, you have to, Charles Adams had some field plates here that you have to get rid of first, but Okay, so this is pretty straightforward. And if I do that, this is an example of the 61D to 62P transition. This is the EIT peak in the center with no microwaves. And when I add a microwave field, it splits. And so I get this pair of peaks here. Okay. So, all right, just looking at this pair of peaks is, I mean, from the point of view of a standard is really interesting. I can measure that frequency really accurately. And I can calculate the atomic transition matrix elements accurately. Since that splitting is the product of these two, I can then immediately get the electric field of the microwaves. So this promises to be a really excellent calibration, absolute calibration for a microwave field. But we're not really interested in making the calibration standard. We want to make a microwave detector. So I'm going to illustrate a way of doing this. There are many ways of, okay, and this is by no means unique. So if I tune a local oscillator to the atomic transition frequency, and I have a signal frequency that's offset from it by the modulation frequency, the presence of the signal frequency effectively amplitudes the total microwave field at this offset frequency W modulation. Okay, so in fact, I can imagine seeing the presence of the signal field at this modulation frequency. So if I fix the probe laser frequency, say here or here, someplace where the red and green traces are, okay, so at the phase when the signal field is subtracting amplitude from the local oscillator field, my EIT signal looks like this. And when it's adding, it of course, it basically increases the Rabi frequency. And so it will look like the red trace. So I have two choices. I could either set my probe laser here, or I could set it here. But in either case, you want to choose a case where you have the largest variation between these two. And so if I fix it there, now, in fact, if let's say I put it here, I will in fact observe a signal that is this big from from the addition of the signal microwave field. So, I mean, and this is, well, this is one of the ways of doing this. So there are many different detection schemes, and I am not about to try to go through all of them. But I believe that sensitivities of 55 nanovolts per centimeter per root hertz have been achieved, perhaps even better. But okay, it's possible to detect very small microwave fields using this technique. And with that, I thank you for your attention.
So thank you very much, Tom. That's an awesome introduction, and I know I have some questions, but I also realized that we've got one of the great things about you is you managed to hold on to your audience. So we started at about 59 and we got 58 participants left. So great job. I would like to invite people to raise their hands or ask questions in the chat for me to transfer to Tom. But while people are thinking about those, whole time I was trying to think about what the right thing to ask you in particular was. And what's unique about the story you just told is you were there through much of the early development of Rydberg atom physics. I saw some great pictures from what looked like the 1970s with a fantastic afro. And I was hoping you could kind of walk through, you know, people often ask why quantum sensors are happening now. What was it between the 70s and the 80s and today that makes a Rydberg receiver in particular viable for the defense world compared to when you were starting out in the field?
Eric, that's a really good question. I think I have part of a patent on detecting microwaves using basically using fluorescence detection. So it occurred to us, yes, almost 50 years ago, that you could make a detector with this. I mean, in fact, the fact that you can detect room temperature radiation, black body radiation, tells you right away that this is pretty sensitive. But so probably the difference is that the schemes that were available at the time were all based on people using these relatively crude pulse lasers to excite the atoms, and either fluorescence or field ionization detection. Field ionization detection is nice, but it's complicated. I mean, well, it's a little bit complicated. And neither of these, I think, offers a prospect of very good bandwidth. If you rely on the fluorescence, the bandwidth will be roughly the lifetime of the Rydberg states, which will be on the order of let's see, they'll be on the order of hundreds of kilohertz for n equal 20, and for the states people are studying now, the bandwidth would be even lower. So there's basically no bandwidth. It's not okay. You can if you don't care about bandwidth and you're willing to use something like field ionization, you could in principle make a detector that will detect one photon. I mean, to make an optically thick detector for microwaves is not hard. Okay. On the other hand, there isn't much bandwidth. Pulse lasers are a colossal pain in the neck. And so the development of CW diode laser, narrowband CW diode lasers was one thing that was really important. And the other thing was that Charles Adams' rather brilliant idea of, gee, can you observe electromagnetically induced transparency by using these stable Rydberg states? That meant suddenly you could basically, using completely rinky-dink apparatus, be making Rydberg atoms. And I think it's the combination of the technological advances that made this possible. Well, and using EIT. I mean, there's no way you can make a fast detector using, I don't think, using field ionization. But okay, those are just my thoughts.
I'd really appreciate that. And for those of us that are, I just want to make sure I've had a chance to advertise the follow-on talk to Tom's here, that our next talk is going to be by Chris Holloway, who, we arranged these talks on purpose because, Tom's just told you the history. He's told you the way that the sensor was developed over time and its general operating procedures. Chris Holloway is one of the best people in terms of implementing the modern day versions of the receiver, as well as the applications studies that go into what those receivers might be used for. So if you're about to drop off the call, please remember to tune in next week so you can see these things in action. I will just tell you ahead of time if he doesn't use it in the presentation. I've seen Chris Holloway play video games. His team played Super Smash Brothers by broadcasting RF through Rydberg atoms, and so that's a particularly fun thing to observe. So I know I've only got you here for a few more minutes, Tom, but the part of what we want to do here is to have the experts in the field talk about where the field is going to go next. What applications do you see as the reason that the Quantum for National Security TAC should pay attention to this technology? Of course, we can measure it for RF fields, but when you think applications of a Rydberg receiver, it's not going to do everything as well as a classical antenna does, but what do you think it's going to do better than a classical antenna?
Well, that's a good question. I would say to me, its potential advantage is detecting low frequencies for which classical antennas become enormous.
Right, and for anyone in the defense or defense industry world, that is a very a big deal that that will get a lot of investment interest if you manage to figure out how to do that well. So I think we're coming to the close of the hour here. I just want to take one moment to throw it back to John and make sure I didn't miss anybody with raised hands or something or questions in the chat. John, can you come off mute?
I've been watching the chat. There's some admiration for the bicycle in the background, but I think we had a nice set of questions here. Fantastic presentation. Thank you. Eric, thanks for plugging the follow-up webinar next week, same time, maybe a different link.
It's an independent registration for each talk. You do have to register independently, but please do sign up. And remember that there will be 2 more Rydberg receiver talks, one about applications and one from a government representative. And then we're going to move on to other types of quantum sensors, specifically atomic clocks, atomic magnetometers, and quantum inertial navigation sensors. So with that, we're at the end of the hour. Remember that these talks were recorded. You can access them online after the fact, but please do reach out to me if you have any further questions or desire to register or join our TAC. Thank you, Tom, and we will talk to you all again soon.
Thank you both, and tell your colleagues. We hope to see you again at a future webinar. Thank you.
Okay, thank you.